Okay, so welcome to lecture 2 of quantum mechanics 1. So this is today will be lecture 2. So before I start, are there any questions from either the previous lecture or from the tutorial?
No, sir.
Or any question in general?
No, sir.
I have a question. Like the black body should it be necessarily black in color or any color would do?
Yeah, that's a good question. It doesn't have to be black in color. What is important here is that in some sense it's an idealization. Okay, so the ideal thing should be black in color because why are we calling it a black body? Because it is supposed to absorb all the radiation that is incident on it. So experimentally, what do? We don't actually have to color it black. What we do is that we have to create a cavity with a very small, uh, entrance through which radiation can go into the cavity. And because of the geometry of the body, the radiation will basically bounce off several times. And of course, at each bounce, there is a non-trivial probability that it'll get absorbed. So because the radiation cannot get out very easily, very most of the time, for overwhelming probability, the radiation will be absorbed. So even though we call it a black body, it doesn't have to be exactly a black color. The way we are constructing it ensures that all the radiation is absorbed. Okay.
You mentioned when the radiation is incident on it. So does it mean if it falls from angle, it can be reflected?
No, I mean incident as in something that falls on it. That's what incident means. So in this case, incident means that a radiation that enters the black body through the little aperture. Okay. So now let me just draw a picture. I think that'll be easier to explain. So you know what we are considering as a black body is the inside of this object. Okay. So we have some box, and it just has to be large enough. And there is a little aperture. So and what will happen is that for most of the radiation that goes in, you know, it won't get reflected. The angle of reflection will be such that it won't be able to get out, right? So it'll be something like that. So so after a few reflections, it'll get absorbed. Okay. So by incident, I mean it's going to be very, very unlikely that the radiation is going to leak out. Okay.
Understood. And another question is about the shell you considered on number of degree of freedom, the shell with
Yeah.
thickness dn. So
Yeah.
what did we do with that thickness of dn? I mean, what was the goal of doing that
Oh, yeah.
shell thing?
It's just it's just what we do when we are trying to uh, compute the volume, right? You suppose you saw that in physics 112 or electrodynamics, you know. So we have a space, and what we're trying to do is we're trying to count the number of points of integer points in that space, right? So essentially what we're doing is, so let me give a lower dimensional example that'll be easier. So for example, if I have, say, a two-dimensional plane, and this is, say, the x-axis is an x and ny, okay? And so what is this? This is basically the points, it's a lattice, it's a square lattice. All the points for which nx and ny are integer, right? And in all direction. So if I take n, x and ny to be very, very large, so I'm just zooming out. So this is nx and this is say ny. And suppose that around here, the value of nx is about 10 to the power 10. I'm just exaggerating, but very large. Here is 10 to the 6 or something, right? So here, so if I take a small interval here, say dn is much, say, smaller than nx and ny, right? So essentially, we can consider delta n to be, at this scale, we can consider, because delta n is so much smaller than nx and ny, we can, consider these guys to be continuous variables, because because nx and ny is so much larger than 1, and we know that the distance between subsequent points is essentially 1. So then what we're doing is that for large values, we are counting how many points there are between two concentric shells, right? Because as concentric circles. So let me draw better circles. So they're actually concentric. Well, this will have to do. So, okay. So we want this, okay, let me do this again. Okay. Right. So because there's 1 point per unit area, if we just calculate the area, we will be counting the number of points. So now the question I want to ask is that, what is the area of this shell? Well, it's going to be the radius of the circle. So if this is, say, n, then it'll be 2 pi n, and then this thickness, which is delta n. So this is going to be the area. Then what is going to be the volume of the whole space? It's going to be this object integrate from 0 to infinity, right? So we're just doing a higher dimensional analog of this. Of course, there is near this region, near the origin, this approximation that, these are all continuous variables. This is not an accurate approximation. But the overwhelming contribution to this integral is going to come from large values of n, right? So we can justify this this sort of approximation.
So why is the upper limit infinity?
Because you can there is no ultraviolet cutoff, right? You can have as many wavelengths as you like inside the cavity.
So the dots of the graph are wavelengths.
Yeah. Number of wavelengths that you can,
okay.
Yeah.
So, and how is this related to modes? I mean, what did you?
These are the modes, right? These are the modes. We are considering each of these the modes.
Okay, got it.
Okay. All right. Any other questions from anyone else, or?
I have a question. I mean, I posted that article on class discussions about the way someone else calculated the density of states and all that.
Okay, good.
They did two things differently, which I think in our calculation canceled out as well.
Okay.
And firstly, they said the standing waves happen at every half wavelength.
Okay.
And the second thing that they did is they multiplied by 1/8. Yeah, that's the article.
Okay. Well, let me have a look then.
Yeah.
So and they got the same result, right?
Yeah, they got the same result we did. Yes.
Okay, so yeah, it must be counting the same modes, but in a different way. But yeah, thank you for. Let me have a look at that. Okay, I think I've seen that way of doing things as well. So it's not like yeah. This is yeah.
Well, actually, my question was that I'm actually curious what we did versus what they did and why we got the same answer. Like, we
Okay, so basically I
did
have to
something
look at
else that was
first.
canonical, right? Yeah. Yeah, I got it.
Yeah, so I'm not sure. Okay, deriving the Arala genes from. Okay, yeah, they did half. Okay, I'm just quickly having a look. Wave number. Yeah, I think from just looking at it very in a cursory way, I think what is happening is that they are just. So for us, the wave number is both positive and negative, and if you yeah, exactly. Sorry, let me have a look at this and get back to you in the next class. I think that would
Sure
be the
thing.
best policy. Okay.